So hello everybody, this is Luboš Pirkl from CFD Support. I'm here in our Prague office with my colleague Radek Máca. Hello Radek.
Hello Luboš.
How are you today?
Yeah, I'm fine, thanks. And how are you today?
I'm also fine.
Great.
So are you ready for the webinar?
Yes, I am. Great.
Okay, and together with us on the line there is Oliver Felde from CFturbo in Dresden. Hello Oliver, are you there?
Hello Luboš, I am here. How are you?
Yeah, I'm fine, thank you. So the same question, are you ready for the webinar?
I am ready.
Okay, very well. So it seems we all are ready. So hello again, hello everybody. Welcome to the webinar on turbomachinery design and analysis. In today's webinar, we would like to show you an easy way how to design a radial turbine from scratch in CFturbo, and then how to simulate and evaluate it in turbomachinery CFD. The webinar is being recorded, and the recording will be made available online on our YouTube channel. And I hope everything works well. In case of any technical problems, feel free to contact us and we will gladly answer all your questions and comments. Please let me start with who we are and introduce us a little bit. So this is me. My name is Luboš Pirkl. I'm co-founder of CFD Support and also a managing director of CFD Support. I'm sitting here with my colleague Radek Máca. Radek is head engineer and senior developer here at CFD Support. And finally, in Dresden, there is Oliver Felde. Oliver is senior manager CAE at CFturbo. He is responsible for consultancy and software development, especially for the implementation of turbomachinery design and related algorithms in CFturbo. The webinar is going to take about 1 hour, depending on the number of your questions and comments. There will be 4 parts in this webinar. In the first part, there will be this general introduction. In the second part, let's call it the design part or CFturbo part, there will be a live example where Oliver is going to introduce CFturbo a little bit, and then he will show a live example of radial turbine design from scratch in CFturbo with final export of the designed model to the turbomachinery CFD. In the next part of this webinar, let's call it the simulation part or turbomachinery CFD part, there will be other live example where Radek is going to show turbomachinery CFD simulation and evaluation of that radial turbine exported by Oliver from CFturbo in the previous section. And in the last part, there will be a Q&A session dedicated to your questions and our answers. So feel free to put your questions during the webinar, and we will answer them later in this webinar. Just take your chance. It's your time. We are here for you. So, okay. So I think we can start with that CFturbo part. So I'm gonna hand over the presentation to Oliver. So Oliver, are you ready for your contribution?
I am ready. Yes.
Okay. So yeah. Also, I'm gonna switch the presentation to you. Actually, I will do it in a moment, right? So yeah, please go ahead.
Okay. First, I'm very quickly want to introduce our company. CFturbo is based in Dresden and in Munich in Germany, and from the beginning of this year we also have an office in the United States. Our main product is CFturbo, a turbomachinery design software, which is a modern and powerful and also user-friendly software tool, and it's meant for the conceptual turbomachinery design, and it uses the latest and state-of-the-art design theory. Right now we have 200 or more than 200 active clients globally. CFturbo is organized in different modules, so you can choose from pump modules, fans and blower modules, compressor and turbines modules, and of course stators and diffusers, and stators can also be vaned. And of course, because CFturbo is a design package also for radial machines, volutes can be designed with CFturbo. Here are the industries that are served, and amongst them are aerospace, automotive, consumer products, energy, oil, gas, marine, mechanical, and process engineering, plus semiconductor industry.
Okay, so now I switch the presentation to your hands. So.
Okay. Okay, now you should see CFturbo, our current version 10.2.
Yes.
And I, as Lubos already said, want to run a demo example, a live demo in which I'm going to design a radial turbine. And the very first thing is the definition of the design point, and I have chosen a design point of the mass flow 72 gram per second, a total pressure ratio of 1.9, and a design point speed of 180,000 RPMs. The fluid to be expanded in the turbine should be air, and the properties should be perfect gas properties, but one can also choose from different real gas models, such as Redlich-Kwong, Ainger-Redlich-Kwong, and so on. Also, because I want to incorporate into the stage a nozzle with blades, I introduce an additional total efficiency of 90% that takes into account those nozzle losses. Once that has been defined, I am guided through the design process in a way that I now can add a new component, and I'm going to start with the design of the rotor component because that's again the central component. In the first design step, the main dimensions are to be defined, or one can also take the proposals made by CFturbo. So it's going to be an unshrouded, of course, turbine rotor with a certain tip clearance. I set it to 0.2 at this point. There are a couple of parameters that can be used to get proposals by CFturbo. I leave them all to the default value. I just want to show you how and where are those defined. If I, for instance, click into that meridional acceleration ratio, then I can show you that we have implemented some approximation function that takes, for instance, the specific speed as an argument and get back some values. Okay, so these are shipped with CFturbo, but you can override them at any time and can adjust those functions to your needs and to your experience. Okay, once these parameters are all set, there's, for instance, the total efficiency that is quite important because that has to be a realistic value. Once that is done, one can press the calculate button and get CFturbo to calculate decent numbers for the main dimensions like hub, shroud, and so on, diameter. But again, I can go here ahead and can override these values because I want to get rid of the decimal places or I want to change it for other reasons. So what I want to introduce later on is a spinner at the nose of the, or at the inlet of the outlet of the rotor. That's why I set the hub diameter to 0. Then in order to compensate this now increased outlet area, I also decrease the suction diameter a bit. I get rid of the decimal places, and then I can check where am I with my design in the Cordier diagram, and how will the averaged velocity triangles look like for that design. Okay, once that is done, the next design step is to define the meridional contour. Here I can set the axial extent to a certain value. I can also right-click and can put exact values on that control points. I can grab the control points of the trailing edge and can position it somewhere. And as I said, I want to create a spinner here right now. I move that hub control point to a certain location, and I introduce another piece of curve, and this is then set to locations that I think of that are realistic. So for instance, that can be at 14 millimeter, and the radius of that point can be 5 millimeter. And of course, that must be a Bezier curve again with a certain shape. And because I want to have this connection tangential, I can click on that. And if I then change the other control points, I will get a shape of the hub here and a certain spinner contour. Okay, relocating the trailing edge will give me a new shape of the meridional contour, and in 3D it will look like this. Here you can clearly see the spinner. The next design step is to define the general blade shape, which is for radial turbines in almost all cases the radial element 3D shape. Also, I have to define a certain thickness of the leading and trailing edge, both at hub and shroud. At the hub, it should be a bit bigger than at the hub. And also, again, I can have CFturbo calculate the necessary blade angles, but I can also get rid of that automatic calculation option and can type in the blade angles that I want to have. Okay, I leave everything to default because it looks quite reasonable to me. Then in 3D, nothing has changed because only the blade angles have been defined yet. Therefore, the next design step is what we call the mean line design step, where the mean surface is calculated. You can see on the right hand side a preview of the mean surface. There are different options to design this mean surface. One is using MT representation of the data. I'm going to switch to a ZT peripheral projection, because then I can directly design the shape of the leading edge, like that, for instance. You see here how I can, where the circles are, how I can shape the leading edge. And if I press OK now, then in 3D I see the blades with zero thickness together with that green surface, which represents the surface that is perpendicular to the flow direction, and which will be at every position a kind of blade-to-blade passage area. Okay, because the blade has a zero thickness now. The next design step is what we call the profiling. Here we have again different options. The simple options is just using control points, and in between the control points, the thickness values are linearly interpolated. I can do that for hub and shroud separately, like that. And because still leading and trailing edge have sharp edges, there is a next design step which is called the blade edge design step, in which one can shape leading and trailing edge. Very often for radial turbine rotors, the leading edge is trimmed with the big diameters, where it is elliptic in shape at the trailing edge. Again, leave everything to default. And if I now look at my 3D model, I see that I'm almost done with the rotor. The only thing that I want to do at this point is I want to introduce a certain inlet extension which is needed for the further CFD analysis. Okay, again, the rotor is ready now, and I want to proceed with the design, and I want to add a nozzle, which is a stator with vanes, but for turbines it's called nozzle. And to this end, I introduce at the inlet a new component, which is a radial bladed stator with a certain extension. After designing the main dimension, it's like the rotor design. I again can design the meridional shape, which is quite simple here because it's a purely radial component. Leading and trailing edge should be straight and should be constant with respect to the radius, and that's why I'm choosing that option and place it somewhere here in the meridional contour. Again, after that design step, the blade angles have to be designed. Here I can tell them again, like in the rotor design, how many blades I want to have and what is the general shape of the blade. Because it's going to be a nozzle with vanes that can be adjusted according to the operational point, I'm going to choose freeform 2D at 5 spans. Again, the blade has to have a certain thickness, and I can define some initial blade angles which might be changed because, as I said, this blades or vanes of the nozzle can be adjusted during the run of the turbine. Okay, in 3D we have now something like that without nozzle vanes, because I'm at a state where only the blade angles of the nozzle vanes are defined. That's why the next step is again the mean surface design step, where I only can adjust one, what we call mean line, because of that blade shape which is freeform 2D. And with freeform 2D, all spans are defined by just one master span. Okay, again, there's a 3D preview, and once I'm pressing OK, I can see now the mean surface of the nozzle vanes. And again, similar to the rotor, The profiling is the next design step, but here I don't want to use the linear simple design mode, but the freeform design mode with leading and trailing edge rounded and with identical profiles from hub to shroud. And if this option is chosen, then one can grab just basic control points again and can shape the thickness distribution in such a way. And if I zoom into the preview a bit, then you see how that would be result. Okay, the last step has to be finished in order to tell the program that the component design is finished, although nothing has to be done there because leading and trailing edge are already rounded in the profiling design step. Okay, and in 3D it looks like this. What is missing now is the inlet volume, maybe an outlet pipe, which is handy for the following CFD analysis. Therefore, I go back again to our meridional view, add a volute at the inlet of the nozzle. The first design step is again just the definition of the outlet diameter and the outlet width, and that should be just match the inlet geometry of the nozzle. That's why there's nothing to be done here. The next step is to define the general shape of the cross-section of the volute. And here it should be round asymmetric in order to save a bit of space. The third design step is the what we call the spiral development area, and one can again use either built-in design rules like the Flider rule, but one can also just have a geometric based design where just the outer diameters are defined, or the first area, and where a certain progression of that radius distribution can be chosen from. I'm going to leave that to the Flider rule because that's a very robust design mode, and it's reasonable for that example. After pressing OK, the meridional view will look like that, and the 3D model will show the volute including the spiral, but without an inlet pipe and without the tongue or the cutwater. And those two things are defined in the very last design steps. So that's the inlet pipe, which can have a certain inlet diameter if a circular inlet cross-section is chosen, and it will also have a certain height. So like 70 millimeter at this point, and because the shape of the spiral is different to the circular shape of the inlet cross-section, one can define a certain position in which that one shape transformed to another one. So I'm going to have 60% set here, and in 3D it's going to be look like that. And as you see, we have a sharp cutwater here, and this is something that can be sorted out in the last design step, the cutwater design step. And here I want to use or choose from the three different design modes: the fillet mode with a certain fillet radius of 1 millimeter. I can have again a preview, a 3D preview of the cutwater, and if I press OK, the model is almost ready. Just the outlet pipe is missing, and that is very quickly added by just going to the outlet of the rotor, define it as an actual motor with a certain length, So for instance, 80 millimeter. Finish the meridional contour. Saving the project, and then, so of course test is the name, and then prepare everything for the CFD analysis. To this end, a solid trimming has to be done. Solid trimming means all the surfaces that define the fluid space of the component are a bit extracted by the cut kernel, and then intersections are being calculated by the cut kernel, and by doing so, a very watertight fluid space is found without any gaps or holes and so on. And that has to be done for all bladed components. And I'm going to do that also for the rotor. And once that is finished, I hope I can do the TCFD export, where geometric data are exported plus a control file that can be read in by TCFD, and then Radek very quickly can start his part. I'm going to have a coarse triangulation with a moderate granularity, just in order to save some time. And if I press OK, you can see the TCFD file, which is the control file, is written, plus STL data that describe the fluid space of the complete turbine. And saying that I'm ready, I just want to show you that the rotor is rotating in the correct direction, and herewith I can give the presentator mode to Radek. Thank you.
Okay, thank you, Oliver, for your design part in CFturbo. So I'm gonna take back the presentation back to me, and yeah. So now it's time to switch to the simulation part. So let me give a brief description what is turbo machinery CFD. By the way, we have switched to TCFD, so now TCFD will be the main name of the product. So yeah, so turbo machinery CFD is a unique software developed by Czech company CFD Support. I would say it's turbo machinery CFD is smart, easy to use, and affordable CFD software. Turbo machinery CFD was designed for simulations of all rotating machinery, such as pumps, fans, compressors, turbines, turbochargers, hydro turbines, etc. Both radial and axial machines, both compressible and incompressible fluid flows, of course. It's based on OpenFOAM. We believe turbo machinery CFD is unique, at least for 4 reasons. So number one would be there is no licensing policy, which means our clients can keep turbo machinery CFD forever, and they can use it for unlimited number of users, jobs, or cores. With turbo machinery CFD, what is paid for is the first delivery and technical support, and later updates and maintenance. This property gives the investment in turbo machinery CFD a permanent value, and also this means that our clients can scale their CFD simulations in a really big way. Number two would be turbo machinery CFD is fully automated, which means all the workflow from the initial data to the final engineering results can be run by a single click or by a single command, and all the process is done automatically, and for this reason turbo machinery CFD is extremely effective. Number three would be we deliver the extraordinary technical support. We keep custom approach to every customer to every issue. We never leave behind any of our clients, and we are very flexible in it. The technical support is unlimited. We support our clients even in matters out of turbomachinery field, for example, in numerical mathematics, physics, CFD theory, IT, or even software engineering. And number 4 would be the real tutorials are included in turbomachinery CFD, so the users they have no doubts about the best practice settings. The real machines are included and already preset, so the user can basically take one of those tutorials and just replace the geometry with his own and modify the settings and run the simulation. Yeah, and also the requirements on the user's CFD skills are pretty low because everything is in graphical interface and very, very smart to work with. Now, there are many other benefits of using turbomachinery CFD. I'm not going to go for all of them. I finish here with my last point that at CFD support, we believe the future of CFD is the automation. In CFD, everything can be automated. The automation is extremely effective. It's even more effective than we expected in the first place. So nowadays, at CFD support, we only think in automated sense, and this brings a huge value to our customers. Yeah, I think it's time for the live examples. So Radek, are you ready for your contribution?
Yes, I am. So please.
Okay, so I'm going to switch the presentation to you.
Yeah, great. Yes. Show my screen. So now I believe you can see my screen, right?
Yes, we can. You can go ahead.
Okay, thank you.
Yes.
Okay, so good and very hot afternoon from Prague to everyone. So I will directly start with working with the TCFD. So I will show you very quickly how the workflow of TCFD is built. So basically we start from the input data which Oliver has just generated. So from this data, from these STL files, from these geometry files, we will define the computational mesh directly in TCFD. Then we run the computation, and at the end we will show I will show you all some visualization tools, and of course the report which is automatically generated at the end, and it contains all important information about the simulation. So basically I will start from the export from CFturbo, which I have saved directly here. So this is what you get from the export from CFturbo. So first, in the STL directory, there is STL files with all parts of the geometry, and also there is a configuration file which contains all necessary parameters for successful running of the CFD simulation. Okay, so to start working with TCFD, one option is to click directly on this configuration file, or you can click basically the icon on your desktop with TCFD with the current version 17.06. So I will run the TCFD program. So we have developed the graphical user interface directly in ParaView, which is an open source and multi-platform application for data analysis and data visualization. So here we are, and as you can see, directly here in the left panel, there is so-called TCFD source, which is used for setuping or to set up every parameter which is connected to CFD simulation and to the TCFD software. So, because we will use the export from CFturbo, so I will find the export from Oliver, which I have stored here, CFturbo export, right? And I will load this Radial Turbine configuration file. So just I will click on apply, And because all steps are already preset, so at the beginning, we will see the input geometry directly here in this render view. Perfect, which is this. So this is the input geometry, split it into 4 components. So it basically follows really the components from CFturbo. So rotor part, vane stator part, volute part, and outlet pipe part. And in the left panel here, we are able to set or modify any parameter which is connected to the TCFD. So basically here we can load, save, or reload the configuration file. Here are several menus defining basic information about the, for example, about the rotation, about the geometry, about the scale factor, because TCFD works with SI units in meters, and if the input geometry is in millimeters, we have to scale it. So using this scale factor, we have to define the physics. So for compressible simulation, compressible; for incompressible, we should uncheck it. Fluid name. So for compressible cases, we usually use air, water, or you can change the parameters of the fluid directly here. You can change the transport model to the constant or to the Sutherland. Next part, you can also pick up the turbulence model you would like to use for the simulation. Sure, an important part, which I have a little bit modified before this webinar. So from CFturbo, you will get the initial and boundary condition for simulation, the designing point. But I have a little bit modified this condition, inlet condition. So I have defined three speed lines. So each speed line holds 1 rotation speed. So the purpose is to generate whole efficiency map for different rotational speed and for different mass flows or for different pressure drops at the inlet and from the inlet and to the outlet. So each point holds maximum number of iterations. Each speed line holds several points to be simulated. The particular inlet boundary conditions are defined in this menu. So basically at the beginning, at the inlet, we define the total pressure and total temperature. And at the outlet, we define a fixed static pressure at the outlet, again for each speed line and for each point. Another part is the simulation, which is important menu. So here we can say which mode we would like to simulate, if steady state or if transient simulation. Sorry. Of course, we should define the number of processors. So because now I am on my laptop, which has just 2 processors, so I have to change it to 2 processors. Some other parameters which is connected to the solver. Numerical order, so first or second numerical order for the simulation, and other parameters, other advanced parameter numerics, and so on. And now I would like to stay a little bit about the computational mesh definition. So basically, to define the computational mesh, I just would like to make some notes because everything is preset, but just I would like to say some basic information about the process of setting the computational mesh. So basically, it follows the procedure, the design procedure from CFturbo. So the overall mesh, the whole geometry is split into separate parts, which we called component, and each component is defined separately by picking the the particular STL files. So for example, if I if I would like to describe this outlet pipe, so I will found the STL directory where I have stored these STLs. I can name this component, and afterwards I will choose the type for the given geometries. So, for example, for the physical outlet, there is simple type outlet from the list. From the wall part, we can set it as a shroud because it is connected to the shroud rotor, but of course we can set it, for example, as a simple wall. And the interfaces which is connected to the other component should be set as inlet interface or as an outlet interface with respect to the flow direction. This setup is nicely depicted in this figure of the topology of the mesh. And for the inlet interfaces, we usually have to connect the given component to the neighboring component. And all the process is immediately depicted here. So if I, for example, by mistake connect this component 4 to the component 1, I will see the topology, and the dashed arrows shows me that something is connected wrongly in a wrong way. So I have to connect it to the neighboring part, which is component 3, and the solid arrow shows me that everything is okay and well connected. So this is basically done for each component. For each part of the geometry, we should define the minimum and maximum. We should define, or we can modify the minimum and maximum level of refinement, which defines the level of refinement of the mesh, of the computational mesh. We can add the boundary layer if needed, and the connection between two components. There are two approaches how to connect it in a numerical sense. So first one is so-called arbitrary mesh interface, which is set by the value 0 here, or mixing plane approach, which is set by a non-zero number. So we can say here, for example, that the vane stator part and rotor part are connected numerically with mixing plane interface using five interfaces. Well, so for each component, we can define the coarsest cell in the mesh by these values, and internal point which tells which part of the geometry should be meshed. Then we have here other meshes, other menus which are connected to the meshing utility. So these are advanced parameters. Then important menu for post-processing. Here we can define the efficiency probes. So it means which interfaces should be used for the efficiency evaluation. So the default is the inlet to the domain and outlet from the domain. We can set automatic post-processing visualization. So first one is blade-to-blade views. So we can set which part of the geometry should be visualized as a blade-to-blade view, and which field to be visualized, and of course which relative radial coordinate should be used to slice this blade-to-blade view, and on this slice all these fields will be visualized as we see at the end of my part. So by meridian average, again we can set the visualization of any field we set here for the visualization purposes. And for example, if you would like to compare several simulations, we can add the graph, which will be afterwards added to the report. Okay, anytime we are satisfied with the setup, we can click on apply to approve the changes, and afterwards we can go directly to the simulation. So if we are satisfied with the setup, we should denote here the settings part, and now we can click here on the TCFD manager, using which we are able to manage the simulation. The process is very simple. In the directory name, we can define the name of the directory in which all the results will be stored. So then simply click on apply. Afterwards, I will just click write case, so all necessary files and configuration files is created and saved to that directory, to this directory. When the case is saved or stored to the disk, we can click run all, which is button which runs every step of CFD process automatically. So basically, it runs the mesh, it runs the simulation, and creates and run the automatical post-processing tools and evaluation utilities. So for example, I can first click on mesh all, or we can build each component separately. So now, as you can see, the component 1 is meshing. All information, what is happening now is here in the turbo machinery CFD output window. When the mesh is already generated, so I will skip here. So here I at the point where the mesh is generated, and I run the simulation before the webinar. So you are always informed which point is actually simulated and what time, an estimated time of the overall simulation, or estimated time for each point. Anytime during the simulation, we can generate a light report. So this is the short version of the report, which show us the current state of the simulation. So for example, here, now the third point from the second speed line is computed, so we can see the flow rate at the moment, residuals at the moment, and the efficiencies of already computed points. So anytime during simulation, we are informed about the state of the simulation. And if I go at the end, which I have prepared here, so at the end of the simulation, which is here, so here you can see that everything is done. So here you can visualize just a part of the mesh. To check the mesh, for example, also of course you can visualize this after the meshing part, not really at the end of the simulation, but also after the meshing part, to check the geometry, and afterwards you can run the simulation. And automatically at the end of the computation, the full report is generated. So you can directly see the results here, or you can go anytime into computed case, which I have here, computed case for the webinar. So here all results are stored, and if I click here in the report directory, so here is the HTML of the report, so you can share it, you can have it online all the time and see the results. So because we have defined 3 speed lines, which is here. So at the beginning, we have overall graphs which show us the efficiency map, for example, the graphs which show us top pressure difference with respect to the flow rate, and other graphs, and then we have bunch of reports for each speed line, which, for example, contains all basic information about the simulation, details about the mesh, details about the Y+, which is important for turbulence model. Afterwards, we have the efficiency values, efficiency graphs, and the progress of the efficiency, the convergence of the efficiency. The same we have for torque for each point, total pressure difference, total pressure ratio, total pressure per interfaces, for example, total temperature difference, and other important values. And then all this repeats for other speed lines. And because we have defined the blade-to-blade view post-processing, so we can see, for example, the blade-to-blade for setup 1. So this is the blade-to-blade view and the slice at the radial coordinate 0.1, so in the neighborhood of the hub. And nicely we can see, for example, the relative velocity distribution and the streamlines. So we can nicely analyze the the flow in the rotor. And and of course the meridional average. So meridional average of static pressure and meridional average of the total pressure. And everything is every information is also included for second speed line and the third speed line. So this is automatically a report which is generated anytime after the simulation, and of course you are able also to make your own simulations, your own visualization. If you click here, where is the button? Here, show results. So using the show results, you can play around and visualize almost everything. So for example, you can make any slice of any part of the geometry. On this slice, you can, for example, visualize the glyphs. The same you can do for the streamlines, for the 3D streamlines. So also this is possible to visualize, and for example, just the pressure contours and or the pressure or the total temperature contours on the wheel. Okay, so I think my time is almost up. So that is all from my side, and unfortunately I have to give the presentation back to Luboš. So Luboš, are you ready?
Yes. Yeah. Thank you. So I'll do it myself, or
okay, great. Yeah, you are faster.
Okay, thank you for your live example. And yeah, so this was turbo-machinist CFD. So the simulation of the turbine, which was designed in CFturbo. And let's move on in the webinar. And now it's time for questions and answers. So please put your questions if you have one, and we are going to answer your questions. So I'm sorry. Yes. So the first question: hi, in default settings, which pressure is calculated, static or total? So Radek, would you answer this static or total pressure question? Yeah.
Sorry, I missed the question. Can you repeat it, please?
It's the first question. In the default settings, which pressure it calculates? Static or total? So would you comment this, or?
Yes, I can. So in the results we can find both fields, both static and pressure. And in the result, inside the report, which I have. Okay, I will go back.
Switch back to you.
Oh, thank you. So if I go back to the report, so the total pressure drop is, I'm in the bed window. Okay, here's the final report. All right, so efficiency are here, and here was the total pressure difference. So usually, and both for the efficiency and evaluations, always the total pressure difference and total pressure values are used. And in the field, you can visualize, which I have, for example, here. If I click on this, and basically here are all visuals or fields you can visualize. So by default, both static pressure and total pressure are evaluated.
Okay, thanks. So the next question is there an option to select which solver it uses for a whole solution and methods for solving pressure and momentum equations? So did you get it, or?
Oh yeah, yeah, we can, because yeah, basically by choosing. So I will found the setting part, which is here. So where is the simulation? Yeah. So basically, by the combination of here of the time management and by where is it? Here by the physics, if you choose compressible or incompressible, you choose the solver for the solution. So for example, for this case, there is the solver TCFD solver, which is built from the raw simple foam, which uses standard simple algorithms for pressure and velocity coupling. Yeah, so at the moment you can't choose the model for solving pressure and momentum equation. So it is done directly in the solver, and there is no way how to define or change the method for solving this. Yeah, so basically compressible or incompressible and steady state or transient chooses the one solver for the simulations, right? So yeah.
Okay, thanks. The next question, what about the mesh at the interface of connected parts? Yeah. Well, yeah, actually, I don't understand this question.
Maybe I can answer it. I can answer.
Okay.
So if I open here, so maybe there is no point-to-point correspondence because all parts are meshed separately, and as I mentioned, there are two options how to connect these two parts. First is arbitrary mesh interface. So it is just a mapping of the neighboring interface on each other, and there is no restriction. Only, of course, these interfaces must lie over, of course. And for example, I can, okay, maybe I'm too slow to visualize it, but there must be only a line, but the mesh of these two interfaces is not necessary to be really same and to have the point-to-point correspondence. And there are two approaches: arbitrary mesh interface, which can connect these type of interfaces, or mixing plane interface, which also can connect these type of interfaces only by communicating with averaging over some slices, over some rings, and so on. So the meshes can be randomly defined,
Okay.
let's say.
Okay. Thank you, Radek. The next question, is it available as open source? I think I can answer this. Yes, when we deliver Turbomachinist CFD to our clients, yes, we give the source code to all those parts which are under GPL. So yes, of course. The next question, what about thermal analysis? Is it possible to check? I think I'm gonna answer this. Not directly. So the thermal analysis, for example, of solid parts of such a turbine, it's not available directly. It can be done in a combination of Turbomachinist CFD and OpenFOAM, because OpenFOAM has solid parts thermal analysis, but it's not available via graphical interface. So you can send us an email and we can give you more info about this. The full OpenFOAM files needed to be reconstructed behind CFD case are present in the export of the CFD-Simulation, or just VTK? Yes, the full OpenFOAM cases are processed in the background. So I think this is quite clear. The next question is it possible to define additional parameters for post-processing? Yes, yes, it is. I would say yes, yes. It can be done in the configuration file, for example, number of spans and these, so and yeah, and others. Which turbulence models can be used? Radek, would you answer these? Which turbulence models can be used?
Oh yes, I can. Do you see my screens? Yes.
Yes.
Okay. So if I go to the setting part, so basically we provide implicitly we provide, let's say, 3 models or 2, K omega SST and a K epsilon, and of course laminar, so without turbulence model. But in general, you can use any turbulence model which is implemented in OpenFOAM, and by scripting module, we are able to prepare the script to set any or for usage of any turbulence model which is implemented in OpenFOAM. So not directly, but it is possible using the scripting, which is simple Python script which modifies the OpenFOAM case and set the given turbulence model, which is implemented in OpenFOAM.
Okay, thanks. The next question also for Radek: is it possible to import model to TCFD from hypermesh? So external mesh question, basically.
Yeah. In general, the external mesh is possible to import. Basically, it is directly here. Maybe I didn't mention the geometry source. You have 3 options: the directory with STL, which is the case of the CFturbo export, then one multi-solid STL file, which is really similar, but all geometries are in one file, or external OpenFOAM mesh. So if the OpenFOAM provides this not export, but the transformation from any export for any export meshing tools to the OpenFOAM, then it can be directly imported here.
Yes. Yep. Okay. What type of interface boundary has been used for this example?
Okay, so for this example, between we can check it, but between the rotor part and the stator part, the vane stator part, there is a mixing plane approach used, and for the others, there is arbitrary mesh interface approach. So there is, maybe we can say, there is a rule of thumb that between rotating components, both approaches can be used, and between the stator, between the non-rotating components, always the arbitrary mesh interface is used.
Okay, so, and perhaps the last question is there an option to add energy equation?
Well, there is energy equation, of course, for compressible case, but to change something really inside the code, it can be added directly within the TCFD, if I understand it well.
Yeah, maybe I will just note that, yeah, it is possible because the source code is given, so you can change the source code if you know how to do that or what to do exactly, so you can change the code and use it modified. So I would say yes for this, but of course we would need to know more details. I think this is it. So as I think there's no question on there's no other questions. There are no other questions. So I think, yeah, we just conclude. So very well. So this is going to be it. So would you guys conclude? Radek, is there anything to say?
I will just to say thank you for watching, and if you have any question, any comment, any remarks, so please do not hesitate to contact us. We are glad to answer all your questions. So I hope we will stay in touch, and we are looking forward to solve any problem you have. Okay, so thank you for watching.
Okay, thanks, Radek. And Oliver, is there anything you would add?
Yes, I just also want to thank the audience for their time. And again, as Radek already said, if there are any questions concerning CFturbo, just use the email address as given and ask whatever is interesting for you. Okay, thank you.
Okay, thank you guys. So okay, so this is it. So thank you for your attention. We are looking forward to collaborating with you. So stay tuned and bye bye.